Lecture, we have discussed commutative laws for union and intersection. Then we discussed associative law for three sets A, B, C. Then distributive laws and proved them. Then De Morgan law for two sets we have proved. And then at last we have solved some numerical based on these results. Algebra of sets. So in this topic we will discuss various properties satisfied by sets. First property is commutative law, that is A union B is equal to B union A and A intersection B is equal to B intersection A. So let us prove these properties. First, by definition, A union B is equal to elements of this are x belongs to A or x belongs to B. Or we can easily rewrite this as x belongs to B or x belongs to A. So which does not affect the elements. So as per definition, what is this? This is B union A. Hence we have proved A union B is equal to B union A. Now second part, A intersection B. Again, by definition of intersection, an element belongs to this set if x belongs to A and x belongs to B. So we have to remember the only difference between the elements are, here we have or, either it belongs to A or to B, but here we have and, it has to belong to both the sets. So this again may be written as x belongs to B and x belongs to A. So again this is B intersection A. So this implies A intersection B is B intersection A. Second theorem, associative law. So that is, for any, let A, B and C sets, we have A union B union C is equals A union B union C. So in the similar manner we have to prove here left hand side is equal to right hand side. To prove this, we start with left hand side, that is A union B union C, which is equals x is an element, x belongs to A or x belongs to B union C, which further imply x is an element if x belongs to A or x belongs to B or x belongs to C, because of union here, which further may be written as x belongs to A or x belongs to B or x belongs to C. So see, by definition this becomes x belongs to A union B or x belongs to C. So again by definition this becomes A union B union C, which is right hand side, hence proved. So similarly we have A intersection B intersection C is equal to A intersection B intersection C. Now third theorem, we have for any set A, we have A union A is equal to A. This is part 1, and part 2 is A intersection A is also A. So we prove this. You see, again by definition of union, A union A contains elements of x belongs to A or x belongs to A. So we can simply rewrite it as x belongs to A. So what is this set? A itself. That's it. Now proof for second part. A intersection A. So that contains x belongs to A and x belongs to A. Does it affect? So we can rewrite it as x belongs to A, which is again A. Next property, distributive laws. Now for any sets A, B and C, so we have A union B intersection C is equal to A union B intersection A union C. So again here we have to show left hand side is equal to right hand side. So we start with left hand side, that is A union B intersection C. So as per definition, this set is x belongs to A. Here we have union, so we get or x belongs to B intersection C. Again applying the definition, this is x belongs to A or, so intersection means and x belongs to B and x belongs to C. So again we rewrite it as x belongs to A or x belongs to B and x belongs to A or x belongs to C, which is further, so this means x belongs to A union B and this means x belongs to A union C, and in all we get A union B intersection A union C, which is right hand side, hence proved. So similarly we have A intersection B union C is equal to A intersection B union A intersection C. Next theorem, De Morgan's law. And for any sets A and B, this law says that A union B dash is equals A dash intersection B dash. So let us prove this. So we start with left hand side again, A union B dash. So we know dash means complement of the set. So this is set of the form that x does not belong to A union B, and which further imply all those elements x does not belong to A and x does not belong to B. So you see, if it does not belong to A, it belongs to its complement. If it does not belong to B, it belongs to its complement, and which further imply x belongs to A dash and x belongs to B dash, means x belongs to A dash intersection B dash. So this is A dash intersection B dash, so hence proved. So another result is A intersection B dash is A dash union B dash. So again we can easily prove this. So we start with left hand side, A intersection B dash means complement means all those elements which does not belong to A intersection B. Now we again start with left hand side. So X is an element of this set if X does not belong to intersection B. It doesn't belong to intersection B means X does not belong to A or X does not belong to B, which further imply that X belongs to A dash or X belongs to B dash, and which means it belongs to A dash union B dash, which is the right hand side. Next result, for difference of sets, for any two sets A and B, A minus B is A intersection B complement. To prove this, we start with left hand side, and by definition of difference of sets, this set is of the form that X belongs to A and X does not belong to B, because we know the definition, all the elements of A which are not in B, which further may be written as X belongs to A, and if X does not belong to B, it belongs to its complement. That means X belongs to A and X belongs to B complement, so it belongs to intersection of both, that is A intersection B complement, hence proved. So similarly, second part can be proved. Now another result, that is for any sets A, B and C, we have to prove A minus B union C is equals A minus B union A minus C. So again we start with left hand side, that is A minus B union C. So here we use the above result. So this is equal to A intersection B union C complement. So here we apply the De Morgan's law. By that law, this is B dash intersection C dash, which is further distributive law applying this intersection C dash. So again using this result here, this is A minus B intersection A minus C, which is right hand side. So similarly, we can prove A minus B intersection C is equal to A minus B intersection A minus C. Let us now discuss numericals based on algebra of sets. And first numerical is, for any two sets, we have to prove union of two sets is equal to intersection if and only if A is equal to B. So we start from left hand side, let union is equal to intersection, and we want to prove this imply A is equal to B, sets are equal. So we can easily prove this, just trying to remind the definition of union and intersection here. So what intersection means? So intersection A intersection B contains common elements of A and B. And union contains elements of A, B and both, as well as common elements. But here the union contains only the common elements, means sets whose union we are taking have common elements. All the elements are common, which imply A is equal to B. Now right hand side, if A is equal to B, that imply A union B is, A intersection B is A, as well as A union B is A, which imply A intersection B is equal to A union B, hence proved. Now another numerical, if A union B is equal to C, A intersection B is phi, empty set, show that A is equal to C minus B. So let us start from C minus B. So using the results that we discussed, this means C intersection B complement. And also we have the value of C, putting the value of C here, A union B intersection B complement. So applying distributive law here, A intersection B complement union B intersection B complement. So is there anything common between B and its complement? No. So this is phi. A intersection B complement union phi, which is again A intersection B complement. And from A intersection B is equal to phi imply A contained in B complement. You see, if A contained in B complement, what is A intersection B complement? The smallest set, that is A, so which is right hand side. Next numerical, for any two sets A and B, show that A complement minus B complement is equal to B minus A. Now we start with left hand side, A dash minus B dash is equal to, we can easily write this as A dash intersection B complement because B dash complement is B. So this may be rewritten as B intersection A dash. Now you see, what is this B intersection A dash? This is B minus A. Hence the answer. So next numerical, for any sets A and B, show that A union A intersection B is A. So we start with again left hand side, A union A intersection B. Now applying distributive law, this is A union A intersection A union B. What is A union A? This is A intersection with A union B. Now just look at this, A intersection with A union B. Now clearly A is a subset of A union B. A is a subset of A union B. So therefore intersection is A. Now to understand this, we will draw a Venn diagram. This be the universal set. This is A, this is B, this is A, this is B. Now just have a look. A union A intersection B. This is A and this is intersection. How much is A union this whole of A? So that's the answer here. Next numerical, prove that A minus B union B is A if and only if B is contained in A. Now to prove this, we again start with left hand side, A minus B union B. So this is may be written as A minus B, that is A intersection B complement union with B, and here expanding distributive law, A union B intersection B dash union B is equals A, and which further imply A union B intersection, what is B dash union B? That is universal set. And what is this intersection with universal set? A union B is equal to A. Just look at this, that union of two sets is equal to A. This is only possible when B is contained in A. So conversely, now if B is contained in A, then we have, now right hand side, if B is contained in A minus B union B is equal to, if B is contained in A, then how much we have from this and this? To understand this, we can draw its Venn diagram. You see, we have, this is A, this is B. What is A minus B? These elements. B, this is A minus B. Union B, whole of A. Union B, whole of A. Hence, this is equal to A, which completes the proof. Now, next question. For any two sets, A and B, show that power set of A intersection B is equal to power set of A intersection power set of B. To prove these two sets are equal, we prove left hand side is contained in right hand side and right hand side is contained in left hand side. To show this, we start with an element of left hand side. Let X belongs to PA intersection B. This is a power set. So elements of this set are again sets. Now if X belongs to the power set of A intersection B, this implies X belongs to A and X belongs to B, which further imply X belongs to power set of A and X belongs to power set of B. So this further imply X belongs to power set of A intersection power set of B. So which means PA intersection B is contained in PA intersection PB. Now let Y belongs to PA intersection PB. So this further imply Y belongs to PA and Y belongs to PB. So which further imply Y belongs to A and Y belongs to B. So it belongs to their intersection. So it belongs to intersection, it belongs to the power set. So which means PA intersection PB contained in PA intersection B. So from this and this, we have PA intersection B is equal to PA intersection PB. Hence proved.